Assalamualaikum warahmatullahi wabarakatuh, Dr. Nur Aimi and fellow classmates. Today, our group will be presenting on the structure of oxide classes as part of our MST512 course. My name is AININ and I will be walking you through the foundational concept and atomic arrangements of these unique materials. Let's get started. This presentation is a collective effort by our team, ADLIN, AIDA, FARAH, HUSNA, Aqilah, AININ and SHAFIYAH. We have divided our analysis into several key sections, starting with an introduction to non-crystalline structures and moving into the divergence between atomic orders. Now, let's move into the technical definition of oxide classes. To understand oxide classes, we must first define them. They are inorganic non-crystalline ceramic materials formed by rapidly cooling a molten liquid to prevent crystallization. This creates a frozen liquid state where the disordered atomic structure of a liquid is trapped in a rigid solid form. Our primary structural benchmark is silica. If you look at the figure, we can clearly compare the two structures. Diagram A shows crystalline silica, which features a highly ordered periodic lattice with uniform hexagonal rings. This is the characteristic of long-range order. On the other hand, diagram B shows our non-crystalline silica class. While it uses the same chemical building blocks, it connects randomly into irregular rings. This loss of translational symmetry is what defines the amorphous nature of class. Next, we analyze the atomic divergence through short-range order and long-range order. Short-range order refers to the local atomic coordination, and interestingly, it is present in both materials. Whether you look at a crystalline cristobalite in figure A or the sodium silicate glass in figure B, both are built from the same localized silicon-oxygen tetrahedral units. The major difference is long-range order. In figure A, long-range order is present because the structural units repeat periodically in three-dimensional lattice. However, in figure B, long-range order is completely absent. Notice the large brown sphere in the diagram. These are network modifiers like sodium ions. These modifiers disrupt the continuity of the silica network and fill the open spaces, resulting in the distorted and highly random arrangement we see here.
Crystalline ceramics consists of atoms arranged in a regular and repeating pattern. Unlike glass, the atomic structure repeats in all directions, forming what is known as long-range order. This repeating arrangement creates a crystal lattice that provides stability and predictable material properties. The highly ordered atomic arrangement gives crystalline ceramics excellent hardness, thermal stability, and chemical resistance. However, because atoms cannot easily move when stress is applied, these materials tend to be brittle and may fracture suddenly.
Okay, now let me explain the amorphous network structure of oxide classes. The basic unit of oxide class is the silicon dioxide tetrahedron. Each silicon atom is bonded to 4 oxygen atoms, and these tetrahedra are connected through shared oxygen atoms called bridging oxygens. Because of this linkage, the structure forms a continuous three-dimensional random network instead of an ordered crystalline pattern. This random arrangement is what makes the class amorphous. The strong covalent bonds between silicon and oxygen give the class network its stability. At the same time, small amount of other oxides such as sodium oxide or calcium oxide can be added to modify the properties of the classes depending on its intended use. In short, the structure of oxide class is strong, stable, and non-crystalline, which is why it has such unique material properties.
Now, let's look at the direct comparison between crystalline and amorphous structures. While they might look identical on the surface, their internal engineering tells a completely different story. First, atomic arrangement. Crystalline solid possess a long-range order, meaning their atoms are arranged in highly regular, repeating geometric pattern. On the flip side, amorphous solids only have a short-range order. Their particles are arranged randomly, lacking any long-term pattern. Because of this, they behave very differently under heat and force. For melting behavior, crystalline solids have a sharp melting point and melt instantly. Amorphous solids do not. They soften gradually over a range of temperature. For fracture behavior, if you split a crystalline solid, it cleaves smoothly along flat atomic plane. But an amorphous solid shatters irregularly into curved surfaces because it lacks of natural structural line. Next, energy and reactivity. Because crystalline structures are perfectly ordered, they sit at a lower energy state, making them highly stable with low reactivity. Amorphous structures are disordered. trapping them in a higher energy state, which makes them less stable and highly reactive. To visualize this, perfect example of crystalline structures are sodium chloride and alumina, while amorphous structures include everyday oxide glasses and polymers.
This slide shows the real-world application of different oxide glass types and why they are used. First, optical fibers. Use silica glass because it has high transparency and low signal loss, making it ideal for telecommunication. Second, laboratory glassware is made from borosilicate glass tube. It's excellent thermal and chemical resistant. Finally, smartphone screen use aluminosilicate glass because it is strong and stretch resistant. In conclusion, different oxide glass composition have different properties, making each type suitable for specific application.
Now I will explain the mechanical and environmental limitations of glass. Although glass is widely used in buildings, bottles, and electronic devices, it has several limitations. First, glass is brittle, means that it breaks suddenly without significant deformation. Unlike metals, glass cannot absorb impact energy effectively, so it shatters instantly when subjected to excessive force. Second, glass is highly sensitive to surface cracks and defects. Even small scratches or microscopic flaw can weaken the material. This defect acts as a starting point for crack, making the strength of glass difficult to predict. Third, glass can experience stress corrosion and environmental weakening. Moisture, humidity, and chemicals can gradually enlarge existing crack through a process called stress corrosion cracking. As a result, the durability and lifetime of glass structures may decrease over time. Lastly, glass has a poor impact and tensile resistance. Sudden impacts or high tensile forces can easily cause it to crack and shatter. Therefore, engineers often use tempered or laminated glass to improve safety and strength.
To conclude our presentation today, let's take a look at the conclusion. Now, for the structure, they have a very unique structure, which is have a disordered atomic arrangement that lack a long-range repeating pattern. We also use network modifiers to tune down their properties, which is allow us to create high-performance material such as heat-resistant labware and also durable screens. And also, as for the what engineers say, we must address the inherent prettiness and also sensitivity to moisture to ensure the long-term stability in our real-world use. To wrap up our discussion on oxide glasses, now let's review a few key questions that highlight the fundamental concept that we have covered. The first one, we look at the core distinction between crystalline and non-crystalline structure, specifically focusing on their long-range order and how they influence their melting behavior. For the second one is the role of network modifiers, such as sodium oxide and how they fundamentally alter the continuous random network of pure silica glasses. And last but not least, the bridge theory with practice by discussing the borosilicate glass in the preferred choice for laboratory equipment, which will also considering the critical environmental limitation engineering must account for ensure its long-term durability.
Take a look out your window. Put on your glasses if you wear them. You might want to grab a pair of binoculars too, or a magnifying lens. Now, what do you see? Well, whatever it is, it's not the multiple layers of glass right in front of you. But have you ever wondered how something so solid can be so invisible? To understand that, we have to understand what glass actually is and where it comes from. It all begins in the Earth's crust, where the two most common elements are silicon and oxygen. These react together to form silicon dioxide, whose molecules arrange themselves into a regular crystalline form known as quartz. Quartz is commonly found in sand, where it often makes up most of the grains and is the main ingredient in most types of glass. Of course, you've probably noticed that glass isn't made of multiple tiny bits of quartz, and for good reason. For one thing, the edges of the rigidly formed grains and smaller defects within the crystal structure reflect and disperse light that hits them. But when the quartz is heated high enough, the extra energy makes the molecules vibrate until they break the bonds holding them together and become a flowing liquid, the same way that ice melts into water. Unlike water, though, liquid silicon dioxide does not reform into a crystal solid when it cools. Instead, as the molecules lose energy, they are less and less able to move into an ordered position, and the result is what is called an amorphous solid, a solid material with the chaotic structure of a liquid, which allows the molecules to freely fill in any gaps. This makes the surface of glass uniform on a microscopic level, allowing light to strike it without being scattered in different directions.